How's it going, guys? Are you ready for more tips and trips from Mr. Burkhart's spare bedroom office? All right, this time we're going to focus on number 3 and number 4. If you look at number 3, okay, the first thing that jumps out to me is they've given me some length measurements, width measurements, and height measurements for a metal bar. Clearly I'm going to use those to make a volume, but what are you going to want to do to those measurements, right? They're currently in centimeters. What are we going to convert them into? Hopefully you remember that it's meters. So that would be step number 1, is change your centimeters into meters. Okay, that's going to make things a lot easier for you. Okay. You know the density of the bar. Now, here's the really kind of tricky thing with some of these buoyancy problems, is they always talk about this upward force. The upward force needed to keep the bar from sinking once it's fully submerged in a certain liquid is 7.35 newtons. That is not the buoyant force. Okay, that is not the buoyant force. That is an additional force needed in order for this bar to be held up by the buoyant force. So if we were going to make a force diagram of this puppy, right? So the bar is fully submerged, okay? I have 3 forces acting on this bar. I have the weight of the bar, obviously, trying to sink it in the liquid. I have the buoyant force, which is equal to the weight of the displaced liquid, right? And then I have this additional force, that lift, and that lift is going to be my 7.35 newtons. Okay? Okay. So, if I'm going to make an equation based on what I have here, these two are working together to oppose this weight of the bar here. So if I write that out, I've got W bar, that's my FG, that's the weight of the bar, is equal to the buoyant force provided by the displaced liquid plus my lift. To break this down one step further, right, the weight of the bar is equal to my buoyant force breaks into the density of the liquid in question, the volume of the liquid displaced, which should be the same as the volume of the bar, okay, times 9.8 meters per second squared, right? Because that's basically going to be the weight of my liquid. So you need the density of the liquid, the volume of the bar, which is what is displacing the liquid, and G, which is 9.8 meters per second squared, because we are on Earth, and that is going to help determine the weight of the liquid. Plus the lift force. Remember, that lift force is going to be 7.35 newtons. Okay? I hope this answers some of you guys' questions on 3, because I've had a lot of them on how to set that one up. For question 4, okay, we're going to do a very similar process, okay? Let's read the question and see if we can set up some kind of force diagram to figure out what we're setting equal to what. So on number 4, I've got the bag and basket of a hot air balloon weighing a whopping 2,224 newtons. They've given me the weight of the gas, and they want to know what is the volume that is needed for the balloon to be lifted, to lift these 45.36 kilogram passengers. So if we draw a force diagram to kind of outline the problem, okay, there's my hot air balloon. I obviously have the weight of the balloon. All right. I have the weight of the gas inside the balloon. I also have the weight. Okay, I'm going to put it alongside, but it belongs right on top of that. I also have the weight of the passengers inside the balloon. Right? So everything's pushing down except for one force. That force is going to be the force of buoyancy. Right? This balloon, the air that this balloon displaces is going to push it up. So when you set up this problem, buoyancy is going to be equal to the weight of the passengers plus the weight of the basket in the balloon plus, oops, missed there, plus the weight of the gas contained. Okay. Some of these are given, some of these you'll have to find, but don't forget that buoyancy is equal to the density of the air, the volume displaced by the balloon, and 9.8 meters per second squared, because we are in fact on Earth. Okay, this is a given number since it's air. To my recollection, I believe it's like 1.25 kilogram meters cubed, but don't quote me on that. Look that up in the notes. There should be a table with that. And I hope this has been helpful, if a little bit longer than usual, tips and tricks.